this town.
Okay.
Hopefully you have an MP4 player. Kind of works on Ubuntu, I don't know about Windows. But I'm sure there's something that will play.
Okay. I'll figure that
You know what that is? It's a mess, definitely. Can you imagine wiring that thing up and then trying to debug it? One broken wire, actually a phone network. It's like that too. That's a CDC 6600. It's decades old. Seymour Cray went to work for Control Data Corporation and had the idea of building a computer out of transistors instead of vacuum tubes, and he built, I think, a 6-bit prototype with transistors, and the thing worked fabulously. It was fast and it was stable, and he got this vision that he could build really powerful machines out of transistors, and he convinced the management of CDC, Control Data Corporation, to let him work on this large transistor-based, very fast computer. And the project dragged on for 3 or 4 years, and they didn't really get any results out of it, and management started getting itchy, and eventually they went to Seymour Cray and they said, listen, we've been giving you all this money and all this freedom, and we're just not seeing the results. We need to change how we do this. We're going to create an oversight committee. We're going to get reports from you. We're going to monitor what kind of progress you're making, and we're going to take over control of this project at the company level. And Seymour Cray's response was, no, you're going to give me a private research lab with a small team of people in a remote location where we can work undisturbed with no interference from the corporation. And if you don't do this, I quit. Bold move. He knew what he wanted. He had a vision of what he was trying to do, and he was willing to take those kinds of risks to make them happen. And in this case, CDC said, okay, you've got it. And they set up a research lab at a very small farm in the middle of nowhere, Wichita Falls. Supposedly, if you got close to the farm, you could tell because on the power lines on the side of the road, there was this extra big cable that was carrying all the electricity they needed to run the equipment in the lab. And had 34 people there, including the janitor, and they just worked, and they built this thing and changed the face of computing. This was the first supercomputer. And it was 10 times faster than the fastest computer in the world. And it was built by 34 people working on a farm. So that was shocking to people like IBM, who had thousands of people working in their labs trying to build fast machines, and got totally bypassed by these people at CDC. And then Seymour Cray eventually left CDC and started Cray Research and built what became the new fastest machines in the world, the different Cray supercomputers. Fast machines, supercomputers, what they do is they crunch numbers, they crunch floating point numbers, they do arithmetic really fast. And that's what we're going to keep talking about today is doing arithmetic in hardware and on computers, looking at different ways to do that. At this point, we're pretty much in the second part of the course, and so we're kind of following things from the book. So this is chapter 3 in the book. We're not going into the same depth that that text goes into. The text is like hundreds of pages. And we're just not going to go into that kind of detail. We may cover some things that aren't in the text, but the basics of what we're going over are from that big textbook. And some of the slides that I'm using, and more in coming weeks, I'll switch over to slides that the publisher provided. So they're not quite as goofy as those other slides. They're actually pretty good. So we're going to continue with talking about arithmetic. Before I do that, homework 2. So first of all, there's a few people that still need to resubmit the circuit. So as I mentioned last time, submitting the circuit file through Angel doesn't work. I can't read it. So either rename it to a text file and submit it through Angel, or just send it to me as an attachment. You can keep how to sort file, and I can get it in an attachment just fine. I know everybody did this because I can see the original files on Angel and I can see the size of them. I just can't download them. The server is blocking it. So get that to me by midnight tonight, okay? Because I need to get these grades turned in. Hopefully that's not a problem. Let me know if it is, but I'm going to close the book on this at midnight. So if you haven't gotten it back to me, make sure you do that. There's a Dropbox where you're submitting some of your assignments, so when you try to submit circuit files, or if you submitted an online version of your homework, you can put it in through the Dropbox, but I'm not passing out grades through the Dropbox, okay, because not everybody submitted that way. So on Angel, if you go to the Reports tab, there's a section to look at grades there, and your grades should be visible. I'll load them in this afternoon, and you should be able to pick up your grades from there. The comments I make on your homework, if you turn it in through Dropbox, those will appear in Dropbox. Okay? So, and if you did the homework perfectly, I generally didn't make any comments. If there was something you lost points on, I tried to make a comment in there about what it was that you lost points for. Okay, on the subject of homework. People seem to be getting it. I was really happy with the homework results, so it was another good job by everybody. There were a few cases where there were some technical issues. People switching a 0 and a 1 here and there. It didn't look like anything systematic. That's fine. There were a few cases, though, where people didn't turn in parts of the problems. Okay, and it could be that you ran out of time. It could be that you decided you needed to spend your time on other things, or it could be that you just didn't know how to get going on this part of the problem. Okay, if it's that third case, come and talk to me. Okay, send me an email, talk to me after class, something. Okay, because what we're doing here is gonna come back the rest of the semester. And when we're talking about instruction set architectures, you don't want to be trying to understand what a truth table is. Okay, you want to nail these concepts now. So if there's something that you're not getting, definitely come to me. Okay, and I'll be happy to take as much time to find a different way to explain it, to listen to what your understanding of it is, and figure out if there's a disconnect somewhere, and make sure everybody's back on track. Okay, everybody in this class can get an A in this class. I have no problem giving out, A's to everyone. Okay, and if you do that kind of performance in this class, it's going to work really well in your future classes. Okay, anything in programming, operating systems, computer security, it's all going to build on this. Okay, knowing what's going on inside the computer and being comfortable with the underlying concepts, the logic, Boolean algebra, and so on, it's going to help you. Okay, so it's really worth trying to nail this down. And if you start your homework early and you get to something, it's like, I have no idea how to make a state machine, right? It's perfectly valid to just let me know. Hey, I have no idea. I was confused in class. I tried to look it up on Google and I couldn't make any sense out of it. Okay, feel free. And that's what I'm here for. Okay, but you have to do that early. You can't do it the night before the homework's due. Okay, or the night before midterm. So start the homework early, and don't be afraid to hit me with questions. Okay, on that note, any questions on homework 3 so far? Yeah?
Do you have a list of those that those students that haven't submitted, or that you weren't able to open the circuit file?
Yeah, I'll have to. Yeah. Let me pull that up. And I've gotten some emails this afternoon that I haven't incorporated into this yet. So if you send me an email, it's probably fine. Yeah, if you came in late and you turned in your homework on paper, feel free to come up and grab it. Okay, Corey, James, Sean, and Kate. I think those are the only 4. And I think I got 2 emails this afternoon. So if you didn't send me an email and you want to send me an email.
On one of those homework problems, the one where you have to do go through A through G.
Mhm.
On here, I think it said A through F,
Oh, really?
and
Okay.
I went A through F.
Okay, that
But-
explains that.
So that's why I didn't do G, but I guess because I wasn't here, I missed the memo.
No, that's
So-
my mistake, so I'll give you back points for that.
I was gonna bring it up right now to make sure that it was actually me that read that like that.
Yeah, no, I saw that, but
Did you?
I just did G to be safe.
Okay.
Yeah, it was out.
Okay, oh, so everybody did. So, A through F there.
Oh, I was
So in
blind.
the rest, two tables showing that each in segments A through F should be set to each input condition. So I
You
just
should
did
get
A
points
through
for
F.
paying attention to the problem.
But
To the wording.
I screwed up and didn't do G.
No,
I just looked
fine.
at the pictures,
Yeah.
that's all to do.
Okay, I'll go back and fix that, that's my mistake, good catch.
So either the entire class, no, I just I say that.
We give extra
Didn't do what
credit.
they were supposed to do.
Okay, yeah, that's fine, I'll change that. Thank you. Yeah, F is really easy.
Oh, I forgot the
On the control 3, you ask about the binary equation for the state machine.
Mhm.
So which form you want?
So which problem?
4, I guess.
Okay, write Boolean equations for each next state in terms of current state and input. So, what did we call our states? Call them S3, so something like S3 equals, I don't know, your state S2 and you got an A, or an S1 and you got an B, something like that. I don't remember what the inputs were. Okay, something that says how you combine the information about your current state and your inputs to figure out what the next state is.
And how do you indicate the final or accept state on the diagram?
We didn't really talk about final states. Initial states you can just sort of point to and say initial state.
But if
You
it,
have to.
if it detects this pattern, then you should like have some final accept state.
Well, this machine just kind of kept running, so
Yeah, the
this
second
is
one.
the combination lock.
For the false assignment.
Yeah, so the combination lock. So just indicate which state means that you've matched the pattern, and after you match that, go back to the beginning. It just keeps accepting input, and anytime it sees 0, 1, 1, 0, it goes to some state that would indicate that you've matched.
Okay.
Just a question, if you input 0, 1, 1, 0, 1, 1, 0, how many times would that open the lock?
Let's say,
Just,
like that.
yeah.
So when you get to this point,
Just once.
it discovers that the lock is unlocked. Okay, you hit the combination.
Mhm.
Then you go back to the beginning,
Yeah,
and you start looking. So this would not actually
okay, good.
unlock it. Yeah. If you make any assumptions like that, just go ahead and tell me what they are, and I'll take that into consideration if something's not clear, or just ask about it.
Looks
That's
clean.
not so good. We've got 8 dry erase markers. I'd like to go over K-maps with this if we need to. Okay, any other questions?
And I tried about think about flip-flops.
Mm-hmm.
I'm not sure I quite understand the difference between D flip-flop, T flip-flop.
Okay.
For how all these details, so they different.
So So should we, we'll stick to flip-flops instead of latches. Because that's most of what we talked about. So,
And what is this now?
so this is a D flip-flop. Okay, typically it's got two inputs. One is D, the other is your clock. All these flip-flops have a clock. Clock is positively edge triggered in this case, and there's an output Q. There's also a Q bar output, we won't worry about that.
So by positively triggered, you mean it's always positive or it changes? Because it's
It changes, but when it changes from 0 to 1, that's when the action happens. Okay, so if you looked at a timing diagram for this,
Negative triggered, it will be from 1 to 0. Okay.
yeah. So, if Q is 0 and D is 1, right, flip-flop is closed, Q is still 0. When the clock raises from 0 to 1, that's when Q changes. Okay, so it's a simple data flip-flop. It just loads in one bit of data and stores it inside whenever the clock goes from 0 to 1. That's the positive edge trigger part. And if you change D, the output stays exactly the same. If you drop the clock, the output stays exactly the same. And the next time that the clock raises, that's when the output changes to match D. Okay, so it's a clock storage device. Every time the clock goes from 0 to 1, D is loaded inside the memory, and it's stored there.
Are your lecture notes pretty explicit on this stuff? So when I go over them, I'll know exactly what's going on.
Not sure. But all this stuff is really standard, so if you go to the wiki, on Wikipedia, and look up D flip-flop, JK flip-flop, it'll tell you more than you want, but somewhere within the first few paragraphs, it'll probably cover everything that I've covered.
D flip-flop and JK?
JK, yeah, JK is the next one that we talked about. It's like a really shoddy register. Okay, JK flip-flop. Has two inputs, J and K, and has a clock.
Thank you.
Okay, if J and K are both 0, the flip-flop doesn't do anything. Okay, the clock can go up and down, and the output just stays at whatever it is. I'm assuming it started off at 0 here. And then I think the order is if J raises to 1, and the clock goes high, then the output goes high. So J is like a set input. And now J can go low. The output stays high. And again, the clock can go up and down, and nothing happens. Then if K goes high at some point, and then the clock goes high, the output drops. So K is like Okay, once the clock is high, if we decided to like drop K and raise J, it's still not going to do anything. Okay, if this was a latch, if this was a set reset flip flop, at this point we'd have the set at 1 and the reset at 0, the output would go high. Okay, if it was a simple latch, because it's a flip flop and it's triggered on the edge of the clock, the only action happens when this clock raises right here. Okay, and here everything is perfectly stable. Okay, that's the difference between a flip flop and a latch. It's edge triggered. J and K are both 1. Remember, in a set reset latch, that was an illegal combination. It set both outputs to 1, I think. In a JK flip flop, if J and K are both 1, you have your clock. And every time your clock raises from 0 to 1, your output toggles. Okay, that's just the way it's built. That condition, J and K is 1, is wired into the circuitry to give you this toggle behavior. And then we commented this is basically a frequency divider. Every 2 times that the clock toggles, this thing toggles once. Okay, and there's also a T flip-flop that's like that, but it's just a just accepts a clock and it outputs Q, and every time the toggle line, every time the clock line goes from 0 to 1, the output toggles. So it's sort of a subset of a JK.
So it has a JK input too?
The toggle flip-flop just has, it acts like a JK where J and K are both 1. But you can think of it as a JK flip-flop where J and K are hardwired to 1. You don't get access to the J and K lines. It's a simpler device that only does this toggling state, as if J and K were both 1. They're useful for building counters and things like that, so sometimes we talk about them just as a toggle. And all these flip-flops sometimes have an enable line. An enable line is just a way to turn this device on or off, basically. So if enable is 0, nothing happens. The output is stable. If enable is 1, then it acts the way you'd expect it to. So it's just gated with the clock input.
So 0 turns it on and
0 is off.
0's on. And 1 enables it. And most of these devices, if you get them in an actual chip form, they have an enable input on them. Multiplexers often have an enable, so you can sort of remove it from the circuitry. If you had multiple multiplexers hooked up together and you only wanted one of them to be active at a given time, you can use the enable lines to sort of disable all the other ones except the one you're interested in. So it's just an extra pin that usually you just tie it up to your power supply, so it's getting a 1, and then everything's enabled. Sometimes they have 3 enable lines on them. It's just more flexibility. Have you ever worked with integrated circuits? I'll bring some in. They're usually pretty small, but they typically look like this. They're little black or gray ceramic devices. They have a bunch of pins coming off the edge. 16 pins or 14 pins are pretty standard. And the packages are completely uniform, so the pins are always 1/10 of an inch apart from each other, and I think 3/10 of an inch in this direction. So it's a standard form factor. So when you build these devices, you might have extra pins left over, and if you've got that, why not use them? So that's part of the reason I think why some of these devices have these extra enable lines or inverted enable lines or things like that. There was a popular series of integrated circuits called the TTL 7400 series, and it was sort of the dominant component line for devices, AND gates, OR gates, XORs, multiplexers, adders, all those kinds of things. They all came in this small set of standard form factors with standard voltage levels and power requirements and things like that. And it was just a line of devices that you could buy to build things. And the early computers, including the Baxter, actually built out of these individual chips, just soldered onto boards and wired up and creating those rat nests like that first picture that you saw. So, and you can still find data books that tell you all the different devices that are available. Most people don't build with discrete chips anymore because it's expensive compared to just making a single integrated circuit, okay, if you're big enough to do that, if you're Intel or one of the other large chip foundries.
And for the exercise 2, you have a T flip-flop. So
Yeah.
what is this circuit? Or it goes from flip-flop to flip-flop. So what does it mean?
Sorry, what's your question?
So you have three flip-flops,
Mhm.
yeah? So it's triggered from flip-flop to its on. So this is the clock.
Yeah, so there's one clock in the top, okay, which that's an external input. It feeds the clock on that first flip-flop.
And that one is enabled.
Yeah, they're all enabled permanently.
Oh,
Okay,
okay.
the enable line is tied to one.
Okay.
And so the output of the first flip-flop feeds the clock of the second,
okay.
and so on. Yeah, these toggle flip-flops, those ones that you actually get in Logic Sim, they also have a T input. And if T equals 1, then it says toggle. Toggle when the clock raises. T equals 0 says no toggle. Okay, so it's another enabled input, basically.
So the only time the clock on a successive part is activated is when the first is enabled, and then
Well,
it goes down from there.
In this circuit, they're all enabled. Okay, all the enable lines are set to 1, and all the T inputs are set to 1.
Okay.
Okay, so all of these are completely enabled. So the circuit looks like this. Okay, and this is Q0, Q1, Q2. Take it a little backwards. I'll write that down. Okay, that's the same circuit, just drawn a little differently. So clock feeds this flip-flop, output feeds this clock, output feeds this clock. And what you're looking at are the outputs from the 3 flip-flops. All right, anything else?
By ignoring propagation delay, does that just mean we're not going to have like that millisecond between changes?
Yeah, you don't need to pay attention to what happens while things are trickling through. The behavior is a lot more complex, and you pay attention to that.
Okay.
But you can just sort of look at it logically and once everything is propagated through, see what the outputs are.
Okay.
There'll be some glitches, you don't have to figure out what those are. You're welcome to if you want to, though.
Extra credit?
Thanks for credit. All right, any other questions? All right. All right, I wanted to actually run through the homework 2 questions, a few points on them, just make sure we're all on the same page. With propagation delays, there was a little bit of confusion when something happens and then something else happens 1 nanosecond later, which is the same as the propagation delay. So let's just work through one of these examples. So it's important here, I wanted you to look at the case where the difference between where A and B changed was exactly 1 nanosecond, okay, which is also the propagation delay. So A and B started off at 1, and let's look at A changing 1 nanosecond before B. Okay, so this is 1 nanosecond. Thank you everybody for making these things legible and lining them up nicely, making it like possible for me to grade it. Appreciate it. So X1 is the AND of A and B. And so it starts off at 1, right? The way to think of these propagation delays, at this point, the input to the circuit is a 0. Okay, input A is a 0, input B is a 1. You know that the AND is going to be a 0. Okay, but it takes time for that result to sort of trickle through the AND gate and get to the output. Okay, that's what the propagation delay is. So even though the input has changed right here, the output doesn't change yet. Okay, it's working on it. It's trying to get to the point where the output is equal to 0. But it takes a nanosecond. So instead of dropping down here, it drops down 1 nanosecond after that input changes. Okay, and that's what X1 looks like. Okay, X2 is just B ANDed with itself, which is just going to be B. So it starts off at 1. But then again, even though the input is dropped to a 0 here, it doesn't come to the output immediately. It's going to take a nanosecond to reach the output. So this is going to continue for another nanosecond, and then the output B will drop. Okay, what about X3? What does it start at?
0.
Starts at 0 because X2 is equal to 1. And when does X3 change to 1?
A nanosecond after X2.
Right. So the input to the inverter changes from 1 to 0. At this point, but it's going to take another nanosecond before the output responds. Okay, and then X, which is X1 XOR X3. So you want to XOR this and this. So they start off high and low, so the XOR of 1 and 0 is 1. Okay, and when you get to this point, the input changes. X1 becomes 0 and X3 is 0. So the XOR there is eventually going to be 0, but it's going to take a nanosecond. Okay, so for the next nanosecond it's going to stay high, and then it's going to drop. Okay, and at this point,
x1 is 0, and x3 is 0. So the XOR is still going to be 0 for another nanosecond. And at this point, you've got a 0 and a 1. So the XOR is a 1, but that's going to take a nanosecond. So it's going to stay low for one more nanosecond, and then it's going to come up high. It's going to look like that. Okay, and this is the one some people had trouble with. So if it's confusing, it might be easier to sort of draw this without propagation delay, and then just shift it by a nanosecond. That would be another way to do it. But then make sure you only use the shifted one when you